This video will outline the details behind combining a sum of sine and cosine functions into a single cosine function. So as a generic fact, a combination of the form a sine of omega t plus b cosine of omega t looks like a single illustration you draw the graph. If you draw the graph of one of these functions, you will get a curve that looks like a single sine or cosine function. It might be off a little bit to the side or whatever. It's a simple cosine function. And the reason why that works is because I can always write that in the following form: r times cosine of omega t minus phi for some values of r and phi. Right, phi is going to be some sort of shift or phase shift in the factor, and r is the amplitude of this full oscillation. What's the idea here? Let's work backwards. I can use the identity that cosine of x minus y is cosine x cosine y plus sine of x sine of y to rewrite r cosine of omega t minus phi as r times cosine omega t cosine of phi plus sine omega t sine of phi. And then by expanding this out, I will get r cosine phi cosine of omega t plus r sine phi sine of omega t. And if I want this to match with a cosine omega t plus b sine of omega t, I can, provided I make these matchups work, provided that I have a equals r cosine phi and b equals r sine phi. Great. But if I have a and b, how do I get to r and phi? Well, the important thing to realize here is if I look at a squared plus b squared, this is r squared cosine squared phi plus r squared sine squared phi. But that's just r squared times cosine squared phi plus sine squared of phi. And this here is 1 because of the Pythagorean identity. This means that I can find r by taking the square root of a squared plus b squared. If I look at, say, b over a, this becomes r sine of phi over r cosine of phi, which is on the side tangent of phi. So I can get phi as the inverse tangent of b over a, being careful about the quadrant that I need to make this work. So I can get from r and phi to a and b, and I can get from a and b to r and phi. It looks like polar coordinates. That's not a coincidence. So how does this relate to our second order equations? Well, if I have my solution of the form a cosine of omega t plus b sine of omega t, we can see that y of 0 is just a, and y prime of 0 will be omega times b. So basically, I can get a and b from the two initial conditions, right? Just y0 and then y prime of 0 over omega, and then r is determined from a and b. So this gives me then that b is y prime of 0 over omega. So tying this all back in, the amplitude of the oscillation that I get from this sort of setup is the square root of a squared plus b squared, which is the square root of y of 0 squared plus y prime of 0 squared over omega squared. The oscillation depends not just on the position at the start, but also the velocity, which makes sense based on a mass on a spring system. If you have a mass on a spring at a certain point, how it behaves is going to depend on whether I let it go. If I throw it upwards or throw it further away, I'm going to get different types of oscillation based on those different parameters of how I'm starting the system. So it's going to depend on both the initial value and the initial derivative for this problem, and we can figure out what the amplitude is going to be just knowing this information. The process here basically comes down to, how do I take the equation I get from a general solution and put it into a form I can actually analyze, and that involves converting into this cosine omega t minus phi form, so I know the amplitude and the phase shift, and I can easily determine what's actually going on and how far it's going to oscillate for this type of a problem.